We're going to be starting on 5.3 now, and that is the fundamental theorem of calculus. Fundamental theorem of calculus is kind of your bread and butter, so we need to know it rather well. It has two parts to it, and basically what's going to happen is the fundamental theorem of calculus. This section is the technique of anti-differentiation that we learned in section 4.9, and we're going to add it to the concept of the Riemann sum, which of course was the issue of area, and we got that in sections 5.1 to 5.2. And once you take those two things, the technique of anti-differentiation and the concept of the Riemann sum, especially in that what I call the bridge section of 5.2, where it basically says, well, that sum is the definite integral, and you'll understand more about what that means here in just a minute. Once you do that, you wind up basically having just the wonderful prelude into the fundamental theorem of calculus. There are two aspects of the fundamental theorem of calculus, okay? And what I mean by aspects is that some books call them two parts. Some books actually label them the first fundamental theorem of calculus and the second fundamental theorem of calculus. And in fact, your book does it in the opposite order that a lot of books do. And I understand why your book does it in this order. Your book does it in the order that I would do it in if I were proving the fundamental theorem of calculus. I am not going to prove it for you. Khan Academy has a wonderful little video. You can go look it up there, and there's a bunch of PDFs from, universities, where they actually want you to know that. This is not one of those proofs that I really think is worth going through or worth burning an entire video to cover, because there is actually a little bit to do before we reach the end of the chapter. But basically what your book calls, basically what I'm going to do is I'm going to be dealing with, gosh, that's ugly. If I have the integral from a to b, and remember a to b represents the interval that we're dealing with, of f of x dx. Remember, the antiderivative of f is f of b minus f of a. That right there is what is usually termed the first fundamental theorem of calculus, okay? But what your book calls fundamental theorem of calculus part 2, okay? It doesn't really matter which one you call it as long as you understand this concept, okay? And we're going to go ahead and go over this one first, okay? And when it comes to the other one, I'll usually refer to it by these titles because that's the way that I learned it. This is the first fundamental theorem of calculus, okay? So really, really easy. Let's say that I have the integral from, let's say, 0 to 4 of x squared dx. Now remember, according to 5.2, when we started talking about equating the definite integral with the Riemann sum, this basically is asking me for the area under the curve of y is equal to x squared from 0 to 4, okay? And what happens here is I need to anti-differentiate x squared. Well, we already know how to do that. That's 1/3 x cubed. That right here is f of x, big F of x, okay? So you just draw a line right here, and you put the 0 and the 4 right here. That's the first step. And basically that says that here is my big F of x, and I'm going to be evaluating it at 4 and at 0. So we have 1/3 times 4 cubed minus 1/3 0 cubed. This right here is f of b, right? Because that's b right here, that second limit of integration. And I need to subtract f of a. Well, that of course winds up being 64/3. That's really not all that difficult. And basically, in terms of dealing with the definite integral and applying the fundamental theorem of calculus, what would have taken us a page worth of sigma notation and limits and finding S of n and sigma formulas and all sorts of fun stuff like that, took us all of about 15 seconds. Okay? And usually, you know, when I was teaching this, my kids would look at me and want to murder me in the same way that, you know, they wanted to murder me the moment I told them how to do differentiation by the rules rather than by limits. But remember that every time you actually do this, you have that limit, that sigma stuff going on in the background. That's actually what's going on. You're accumulating the infinite number of cross-sections that have a width of dx. Dx takes the place of delta x with a height of x squared. So this is your f of x sub I, and this is your delta x, and this integration formula, this integration symbol right here, this notation, takes the place of limit as n approaches infinity of the sigma, okay? And basically, that's it. I mean, that is a really, really straightforward and really, really easy example. Let's do another one. Let's say that I want to find from 0 to pi over 4 the integral of cosine x. Now remember that when we're anti-differentiating, we're figuring out what is cosine the derivative of. Well, cosine is the derivative of sine, okay? And that shouldn't really be all that difficult, so I need to put sine x right here, put that straight line up and down, and basically that helps me to keep track of my limits of integration, right? Because what I'm really interested in right here is if I'm looking at the cosine graph, I know the cosine graph does that number, right? And it crosses right here at pi over 2. So really what I'm looking for is I'm looking for this area right here between 0 and pi over 4. And so I anti-differentiate what's called the integrand, right? You know, kind of like the thing that is underneath the radical is called the radicand. Well, the thing that is sort of the object, the thing that is being integrated is the integrand, okay? Integrand, A-N-D, just like radicand, right? And then, of course, I have to evaluate sine of pi over 4 minus sine of 0. Well, sine of pi over 4 minus sine of 0 is root 2 over 2 minus 0, or root 2 over 2. So that area right there, that shaded region right there under the curve, cosine x, on the interval 0 to pi over 4, is actually 0.707, half of root 2. Okay? Now that is the first fundamental theorem of calculus in the nuts and bolts. So let's do a couple of problems that are maybe a little bit more aggressive. Okay? Now remember, when we were dealing with derivatives, and I asked you something like, what is the derivative of natural log x? That became 1 over x, right? So what do you suppose the integral of 1 over x dx is? Well, it's actually natural log of the absolute value of x, of course, plus c, because this doesn't have limits of integration, right? And of course, you're asking yourself, why don't we have the plus c? Well, we'll get there here in just a second, okay? Now remember, the reason why this has absolute value bars on it is natural log of x, by its very nature, has a domain of 0 to infinity. That's y is equal to the natural log of x. And I know that the derivative is there to describe natural log of x, okay? And therefore, the derivative must exist at least on the same domain. Well, 1 over x exists on 0 to infinity. Now, it also exists on negative infinity to 0, non-inclusive. But we don't really worry about that because you really only ask questions about natural log of x on the domain of natural log of x. Now, the integral of a function, and of course you're taking the integral is an operation just like the derivative is. the integral of a function needs to describe that function on its domain. Well, if y is equal to 1 over x has a domain of negative infinity to 0, union 0 to infinity, then its integral, okay, must also have that same domain, and that absolute value of x takes care of that. That absolute value of x basically means that this is y is equal to the natural log of absolute value of x, because basically, remember, when the absolute value, when we're dealing with transformations, the absolute value on the input evens the function, so it winds up having y-axis symmetry. Okay, well, all that to be said, let's go ahead and do y is equal to 4 over x, and I want to find the area under the curve on the interval, let's go 1 to 4. Okay? Well, that means that I need to set up the integral 1 to 4 of 4 over x dx. Now remember, that constant can be pulled out in front, and I can go 1 to 4 of 1 over x dx. Okay? Now, that means that I have 4, and we can go ahead and do natural log absolute value of x from 1 to 4, right? And you're saying to yourself, well, what about the plus c? When we were dealing with it in 4.9, and we were dealing with, sorry about that, and we were dealing with antiderivatives, there was always a plus c. Well, you got to remember that an integral is an implied difference. So if you put the plus c is going to just be subtracted from itself the moment that you turn that into a difference. Right? So if you were instead, let me get a pen of another color, if you were instead to actually put in natural log x plus c from 1 to 4, what would happen is you would get 4 natural log of 4 plus c minus natural log of 1 plus c. Well, what happens to that c and that c? Well, they wind up getting crossed out. I mean, they're additive inverses, right? Once you distribute that negative. So we just don't even bother with it. When we're dealing with the definite integral in the fundamental theorem of calculus, we do not deal with the plus c. The plus c is only for the indefinite integral, okay? And we'll get to that shortly. So we have 4, and then of course this is an implied difference. We have natural log of 4 minus natural log of 1. Well, natural log of 1 is 0, and so that's 4 natural log 4, or if we want to be really, really tricky, that's natural log 4 to the 4th, which you don't have to do. But that basically right there is the area under the curve of y is equal to 4 over x on the interval 1 to 4. And you use the first fundamental theorem of calculus in order to actually arrive at that value. Okay? Now, let's go ahead and do... actually, let's go ahead and call the first video to a close right about now. That's basically what's going on in terms of the first fundamental theorem of calculus. I'll gather some really neat problems, and we'll do just as many as we can in the next couple of videos, and then I'll introduce the second fundamental theorem of calculus, and you'll see why I'm doing it in this order. Like I said, if I was going to prove them, I would do it in the opposite order, but if I'm going to demonstrate them, it's actually better to do it in this order. Couple more videos. I don't know exactly how many, but we'll just sort of play it by ear.